one of the benefits of studying all these different techniques and learning some of the more advanced ways to apply calculus is that we can go back and do some of the things that we did before and apply these techniques to streamline the process. For instance, we used to be able to do implicit differentiation. If we had y was a function of x and you had some expression that had x's and y's all over the place, like in this case, we could do a standard implicit differentiation and we could solve for y prime and we could get a function that was in terms of y prime, and that would, again, we could always do that and we'd have some jumble there and we could implicitly differentiate. But what if we use some of the techniques that we learned so far? So one cool thing is that if we take an equation, or we take some sort of equation, and we know that y is a function of x, and we set everything on one side of the equation, then we can take the partial of this left-hand side with respect to x, and we can take its partial with respect to y, divide them by each other with a negative sign, and that actually gets us the same result as if we had done implicit differentiation the other way. This is extremely convenient because there's a lot of cases where you end up with some nasty behaviors, and just being able to do it in terms of partials can really save you some time. But we're going to do it both ways to show you that we're going to get the same result, and one of them is going to be a little quicker than the other. So let's go and find dy dx for this thing. So I'm going to start out doing it the way that we learned in introductory calculus. And so to do that, we apply the differential operator across everything. So we take the derivative of this with respect to x, and then we take the derivative of this with respect to x. So this is actually x times a function, so you have to do a product rule. So you take the derivative of the first element, so derivative of x is just 1, so minus y, and then you take the derivative of the second thing, well, y there, so we would say minus x dy dx. So then we have to take the derivative here. Well, y is a function of x, so this is like a power rule to y. Well, the derivative of y is dy dx equals derivative of x is 1 and the derivative of y is dy dx. So then we need to get everything we need to get all the dy dx's on one side and all the not dy dx's on the other side. So we end up with that we factor out a dy dx, and we get dy dx equals 1 minus 2x plus y all over negative x plus 2y plus 1. So it's not the end of the world. It's not the hardest thing we've ever done, but there's a lot of bookkeeping here. We have to keep up with these dy dx's. So let's see if we can't do it with this new method and see how quickly it comes out. But there is one gotcha here. Notice that we have to get everything equal to 0. So before we can even go forward, we do have to do one algebraic step and move everything to one side of the equation. So I have to say x squared minus xy plus y squared minus y, or minus x plus y equals 0. And that's not too bad. That gives me my f function on the left. So if I take the partial of f with respect to x, well, that's 2x minus y minus 1, right? Because y squared and y, they're constants, so they derive to 0. If I take the partial with respect to y, I get 0 minus x plus 2y, 0 plus 1. So my result is dy dx is negative 2x minus y minus 1, negative x plus 2y plus 1. If I distribute the negative across the top, I get dy dx is negative 2x plus y plus 1 over negative x plus 2y plus 1. So I have the same denominator, and I have the same numerator, I just wrote it in different terms. But notice this is a lot cleaner because you, by definition, you get your numerator and denominator right here. You just draw you a line, add a negative. And that's really how you do it.